Morning, my name is Gerardo Hernandez, and together with my teammates Jesus Hilario and Adrian Jared, we will present our integrative project on information source modeling, compression, and transmission for seismic data. Our case study is the MW 70.1 Puebla Morelos earthquake that occurred on September 19, 2017. This project integrates 9 fundamental activities into a complete processing pipeline. Our information source is the 2017 Puebla earthquake. The mathematical model follows chapter 10 of the textbook, where the seismogram is the convolution of three filters. First, the source time function S of t uses the Brun model with moment magnitude 7.1, a corner frequency of 0.088 Hz, and a source duration of 4.66 seconds. Second, the air transfer function g of t includes the direct P wave, the PP reflection at the 11.2 seconds, and the SP reflection at 16.2 seconds. Third, the instrument response I of t corresponds to station TJUH in Costa Rica with a broadband response from 0.01 to 10 Hz. As shown in the figure, the synthetic seismogram in black matches the observed data in gray, validating our model. For a statistical description, we segmented the synthetic seismogram into 10-second stationary windows with 15% overlap, yielding 74 windows. The augmented Dickey-Fuller test confirmed the stationarity for most windows. The partial autocorrelation function shown here reveals significant spikes up to lag 13, indicating an autoregressive model of order 13. The AR model represents the seismic signals as a linear combination of its 13 previous values plus white Gaussian noise. We extracted the AR parameters for all 74 windows, resulting in a 74 by 14 parameter matrix containing 13 AR coefficients and the innovation variance. These parameters become our symbols for compression. Each AR coefficient was uniformly quantized to 4 bits, giving us 16 symbols levels. The first order entropy for phi 1 is 2.61 bits per symbol, while the fourth order entropy is 2.55 bits, representing a 24% reduction due to statistical dependencies between symbols. Using inverse transform sampling, we generated 10,000 artificial symbols for each of the 14 parameters. The maximum error between the original and generated distributions was 0.74%, well below our target. This figure shows the close agreement between the original and generated symbols. Jesus will now present the lossless compression results.
Thank you, Gerardo. My name is Jesus Hilario and I will present the lossless and lossy compression results. For lossless compression, we implemented static Huffman and Shannon-Fano coding. For the phi1 distribution, both algorithms achieved identical performance. The entropy is 2.61 bits per symbol, and the Huffman average code length is 2.62 bits, giving us 99.7% efficiency and a compression ratio of 1.53 to 1. As shown in the table, the most probable symbols receive the shortest codes of only 2 bits, while less probable symbols receive longer 4-bit or 6-bit codes. This demonstrates the fundamental principle of entropy coding. Adaptive methods perform worse due to our small datasets of only 74 symbols. Adaptive Huffman achieved a compression ratio of only 1.08 to 1 with 7% space saving. The main issue is overhead. For each new symbol appearing for the first time, the algorithm must transmit an NYT code plus a 4-bit fixed code. Arithmetic coding achieved an impressive theoretical compression ratio of 4.62 to 1. compressing the 74 symbols into just 64 bits. However, in practice, the probability model must be transmitted as site information, adding about 44 bits of overhead. LTW actually expanded our data, achieving a compression ratio of 0.82 to 1. With only 74 symbols, the algorithm could not learn enough repeating patterns. For larger seismic datasets, these adaptive methods will perform much better. This table summarizes all lossless compression methods. Static Huffman is the clear winner for these small datasets, achieving 99.7% of efficiency, and arithmetic coding wins theoretically but requires site information. Adaptive methods underperform due to the dataset size. For practical applications, we recommend static Huffman for offline archival storage and adaptive Huffman for continuous streaming applications where the overhead amortizes over long sequences. For lossy compression, we apply the Max-Lloyd algorithm to find optimal reconstruction levels. At 1 bit, the Max-Lloyd quantizer achieved 9.65 decibels SNR, which is 92% better than uniform quantization. At 3 bits, we achieved 21.11 decibels SNR with a compression ratio of 10.67 to 1 relative to 32-bit floating point. For the 3-bit quantizer shown here, 89.7% of the samples fell into the two highest reconstruction levels, both representing positive amplitudes. This reflects the skewed distribution for our seismic signal, where the most energy is positive with occasional large negative spikes. The improvement over uniform quantization diminishes as a bit rate increases, from 92% at 1 bit down to only 5.4% at 5 bits. Now, Adrian will now present the channel modeling results.
Thank you, Jesus. I will present the channel modeling and system results. We send all compressed signals through three channels types using 16 PC key modulation. First, the LW-KN channel, an ideal case with no fading. This achieved 3.17 bits per symbol. Second, the region channel with strong line of sign like a direct path. This achieved 3.35 bits per symbol, about 18.4% efficiency. This is realism for most seismic stations. Third, the Rayleigh channel with no line of sync. This performed poorly with online 2.26 bits per symbol, and the key point or source rate after compression is 2.62 bits per symbol, is less than the region channel capacity. Relay transmission is possible. Our complete system has 6 stages: source modeling, AR extraction for bits, quantization, Huffman, compression, Marshall quantization, and transmission over region fading. Total compression compared to 32 bits data is 12 bit to 1. We reduce data size by 12 times while maintaining good quality at 21 decibels SNR. Our source rate is 2.62 bits per symbol, and the channel can handle 3.35 bits. This leaves extra capacity for error correction. Here are our main findings. First, the AR model of order 13 captured the earthquake dynamics well. Second, stating Hammond achieved 99.7% 7% efficiency. Third, Matzloy gave us 20 decibels quality at 3 bits. Fourth, the recent channel performed well enough for relief transmission. Recommendation: for a cheap storage, use static Hammond with 3 bits max. Lloyd skipped 22-1 compression. For real-time transmission, maintain S-in-R above 15 decibels. For low is-in-R environments, reduce modulation complexity or add error correction. The main limitation is our small dataset of 74 windows. Future work you should test larger datasets. Thank you for your attention. We are ready to answer any question.